Okay, so for this one, what does that read? 0.325, and then yes, that's going to be a 13 thousandth, so 0.338 inches. How many of you had that? Good deal. How about over here? So 1.1, because that's 1 whole inch, 1/10, then 42 thousandths, 1.142. How many of you had that one? Okay, good. So it looks like we're doing pretty well on those. Actually, I want to do this now. I want to get down to one of these. I'll do the same here. So over here, take a couple minutes, figure out what these two each read. These are metric now. So for this one here on the micrometer, what's this one read? Exactly 9. Perfect. Because it's 6, 7, 8, we're past the half mark, but the fact that it's the 0 means it's right on the edge of the next mark, which would be the 9. So what would this one read? Careful. Oops, over here, yeah, this is 52 millimeters. This is 50.41 millimeters. Perfect. So how about back on this one then? If I make this one into a metric, or in a little bit different reading. Still metric, but different reading. What does that one say? 14.03. Very good. Millimeters. Any questions on any of those?
What? First one, 14 again?
Because you have the 10, but then you got 1, 2, 3, 4. You got the slash marks. Do you want me to pull it back up?
Yeah.
Okay. Oops, that's not it. Micrometers. There we go. No, that's not the one. That's the one. Because you have 10, 11, 12, 13, 14, and then 1, 2, 3. That's the one that lines up is the 03. So 14.03. Another question here. Let's do another one while we're here. Why not? So this one. Perfect. You got 15, 16, 17 and a half, so 17.5. And then this is 35, so 0.35. So 17.85 millimeters. Now, just for the heck of it, what do you get out of that one? Other than a headache? Well, there's 3 scales. How do we know which scale to read? That's on the 16 setting, so we are looking at that. Yes. Then we have to decide what each space on that scale is. Depending on the setting, each space is different. Because you may have noticed, if we were on the 24 setting, between 26 and 28, that's 2 whole units. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces. If you're on that setting, each space is 0.2. If we're on the 0.8 setting, from here to here is just 1 unit, and there's 20 spaces. So that'd be 0.05 is each space. And then, of course, on the 16 setting, from here to here is 1 unit, and there's 10 spaces, so that's 0.1 units per space. Yeah. So this is 13.1234, 13.4. So you were correct. And that is DC volts, that's V. Any questions? Just a little, I mean, I figured you guys could handle the regular scales. That's why we haven't gone over them in class. But just a little check to make sure you've got them. Something you guys might actually run into. Since we're looking at them, why not? The depth indicator. Either a depth or a surface gauge. Some people would call it. Basically, this guy's just a little button. Generally, it's just a little button down here that sticks out, and that hits the surface, and it tells you in or out how far it is. These can read positive or negative, whether it's being pushed in or pulled out, or usually it springs out, so whether it's past its neutral point. Looking at this arrow is telling us that when we engage this, the needle went that direction, so that tells us we're going in the positive direction. Then we got to look down here at this little indicator. Now this one is in millimeters, so this is saying whole millimeters, 0 whole millimeters, so 0.0. And this is 17, you got it. This one here, it's in the negative direction, so it's negative 1, 2, so 2 whole millimeters. Is this 0.19? 8.1, very good. We're reading in this direction, so 1, 2, 20, or 10, 20, 30, 40, 50, 60, 70, 81, 2.81 millimeters. So even though that's on the 19, we're reading it the other direction. That's why it goes from 0 to 50 in both directions. As you go past 50, you've got to figure out what it is.
Where do you get the 2? There's a little dial.
Yep, this little dial here is between the 2 and the 3. So it's not to 3 yet, so it's just 2. So here, positive or negative? Negative. Any whole millimeters? So negative 0 point, that is 29. So 0.29 millimeters. This one, positive or negative? Positive 1, this is between the 1 and the 2, point 50, 60, 74, right? Yep. Otherwise, when you use the gauge, you would watch to see which way the needle went. Yes, you could use it on the lathe. So this one, do you see a change here? You'll see decimal points down here would be the first indicator instead of just whole numbers. You look closely, you see this is 0.001. This is now an inch indicator. So what we get down here is not whole millimeters. This is tenths of an inch. So it's a positive 0.1. Yeah, that's at 10, so 110 inches. It's 110 thousandths. This one, negative, because we're going that way. 0.9, or no, it's not quite to 0.9 yet. How do I know it's not to 0.9? Because this is almost a 80, not quite back to 0. So this is what, 78. So negative 0.878 inches. This one, positive or negative? Positive 0.4. 0.437. And this one, negative. Oh, 59, you're right. So negative 0.159 inches. And then this is just more scales as a vacuum gauge. Because of the way they read, this is 0.5, 1, 0.5, or 1.5, 2, 2.1, 2.2. Very different scale here. That's 50. This is 25, 30, 35, 40, 45, 50. So that is at the 40. My guess is that is not in volts, that's in millivolts. Here's an interesting one. What's that? Well, it doesn't say, it just says DC, but you're not going to use a small meter for 250 volts. So I'm pretty sure, put it that way. This one, an ohm meter reads backwards. It goes from right to left instead of left to right. And you can see the scale changes. Here, each mark is 0.2. Here, each mark is 1. You get up in here, each mark is like 5. And then up in here, each mark is 10. And then pretty soon, each mark is 100. And so the meter changes, the scale changes. It's just the way the mechanics inside the meter work. They're mechanical meters, not electronic meters. And so the way the materials, a lot of the old meters worked on materials, where if the material warped based on something happening, like your old thermostats and stuff based on were two metals pressed together and they would warp as they heated up because one expanded faster than the other. Similar types of things in a lot of these meters were based on physical reactions to an electrical phenomena. And because of the physical reaction of that material, it changed. The higher the resistance got, the less it started to move. Rather than to adjust the material to make it react in a linear fashion, they just adjusted the scale to make it match up whatever the material did. So this is actually just 12 ohms is what that's reading. Whereas something like this is reading, well, that's 100 and that's 150. So this is like 125 ohms, 120 ohms actually is what that's reading. Well, yeah, you got to really get in there and see especially since this has been copied and pasted and then it's up on the projector, it's a little fuzzy for you guys, I'm sure. Like that one there is actually right on the 1000 ohms. Kind of weird that that's 120 and that jumps all the way to 1000.
What would you measure?
That's resistance in an electrical circuit. Now again, these are old. This is an old analog meter. We wouldn't use a meter like this very often anymore. We would still use a digital meter now, which would just give you a digital readout. Where a gauge like that would be in something where it needed to be continuously monitored. So like if you're at a monitoring station in a power plant, you don't want digital readouts everywhere. You want needles where you can just kind of scan across and you know that, okay, these needles are supposed to be straight up and towards the middle of the dial, or this one's supposed to be off here a little bit, so you can just look across and say, oh, that one's in the wrong direction. That one's pointing off to the left. Something's wrong there. A lot of times they'll even have like a color code of some sort. So this part of the dial is labeled green and this part of the dial is labeled yellow for caution, and this part of the dial labeled red for uh-oh. Yeah, pretty much. Red for shut something off or get the heck out of here. Huh?
I still use an old meter, but I only use it to double check to make sure I have a circuit there.
Oh, with the continuity basically?
Light bulb to make sure it's
Sure.
still got a filament.
Yeah, basically just a continuity test. And see, I use the digital, but the problem with digital is you need batteries in them. And they run out of batteries fast. If the batteries get low, they don't necessarily stop working. They just start giving you funny readings. The old analog meters, they still took batteries or they plugged in, but they either worked or they didn't. They didn't give you funny readings and the batteries got low. So something like this. Let's see if you can remember how to read it. Negative. There we go. Negative 0.056. How about this one? Negative 2.58. That one is millimeters. Okay, enough of that fun. I think you guys want your quiz on your calipers and micrometers, right? Sure. Good attitude. Okay, so some of you are still working on the quiz, and that's fine. Take as much time as you need to finish up. We're going to take a look at some of our new material. What we're going to look at. Remember, we talked about areas and stuff earlier. We started out with this location, that point. And we took that point and we pulled it in a single direction. And the distance that we pulled that point defined the length of that line segment. And we talked about how it's technically called a line segment, but in practice it's just called a line. So we're going to just call it a line. Technically a line doesn't have length, it has an infinite length. So measuring the length of a line is pointless. And then we took that line segment and we pulled it in the second direction, perpendicular to that first direction. In fact, we even noticed that it didn't have to be perpendicular, but for what we did, it was perpendicular, formed a rectangle. And the area was defined by that original length times the new distance that it moved. And that was often, the distance was called a width if it was a rectangle. So if this was 12 feet long, and this was 5 feet that we moved it, the area was 12 feet times 5 feet, or 60 square feet, or 60 feet squared. The reason we put distance in here, though, instead of width is because it's not always a rectangle. Because sometimes we're not moving perpendicular, but the distance traveled is still measured perpendicular. So if we take that original 12-foot length and we still move it 5 feet, even though it moves off at a slant like that, it's 5 feet away from where it started, its area is still 12 feet by 5 feet, or 60 square feet. So that's why I avoided using length times width, is because it's not always the width. Sometimes it's just a distance from where it started to where it stopped. And we even looked at how it didn't even have to move straight. It could move at a weird curve thing like that if we wanted it to. Just as long as it always stayed parallel to where it started, and we measured the distance from where it started to where it stopped along that perpendicular. So our next step is, let's take that area, let's take that rectangle, and this is a rectangle here. We're just looking at it from above and off to the sides. It kind of looks weird like that. And let's say that this is 14 inches and this over here is 8 inches. Of course, it has an area of 14 times 8. Or, what is that, 112 inches squared. And now we're going to take that area and we're going to move it a second direction, perpendicular to both of the first two directions. And it's going to create a box. We've moved it now in 3 directions. We've created something that has 3 dimensions. And of course, we're looking at a volume. And the size of the volume depends on the area of the base. We're calling that the base because that's the shape that we grabbed onto and we moved to create this object, this solid. So this is really the area of a base. So the volume depends on the area of that base times the distance that it's moved. Sometimes it's the height, but I hesitate to call it a height because in this case it's a height, but it's not always a height. So for this, let's say that this is 10 inches that it moves here. So the volume is that area of the base, 112 inches squared, times that 10 inches that it moved, or 1,120 inches squared times inches is inches to the third, or inches cubed, cubic inches. Now you might be wondering, why didn't I just say that volume is length times width times height? Well, that is basically what I said, because the area of the base is just length times width, and that distance is the height. But this only applies to boxes like this. What's called a rectangular prism is the technical word for it. This formula can apply to any solid object. First of all, the base does not have to be on bottom. The base is the shape that the object's based off of, not that what it's setting on or anything like that. For example, for this one, the base of this is not the bottom. The base is this triangle here. Why is that the base? Because that's the shape that this is based off of. There's 2 ways you can think of that. One is the shape that I can grab onto and slide throughout the whole object. It's the shape that I grabbed onto and pulled to create the object. Like we're talking about moving that rectangle. Second, if I cut this, let's say I slice it right across here, it's the shape that it produces. It produces that triangle. So it's called the cross section. If you slice it, that's the area of that cross section from where you sliced it at. So when I'm going to find the area of this, the area of the base is the area of this triangle. So that's going to be 12 inches times 5 inches. And of course, since it's a triangle, I got to divide by 2. So 30 inches squared. So now my volume will be the area of that base, 30 inches squared, times the 20 inches. Notice the 20 isn't a height anymore because it doesn't go up and down. It's a distance from where the base started to where the base stopped. Yeah, it's the depth in this case. Basically, it's a distance between bases because these solid objects have a base on each end, whether it's top and bottom or it's front and back or left and right, whatever. So this is going to, of course, going to be 600 cubic inches or inches cubed. So here, length times width times height would not apply. Doesn't work. Also, we can run into something like this. Here, what's my base? The circle, because that circle is what pulls through the whole object. Or if I slice this, I'm still going to see a circle. That's my cross section. So the area of my base is going to be the area of that circle, which is going to be pi times 4 squared. Radius of 4 if it has a diameter of 8. So that's going to be 50.24 inches squared. So now my volume, 50.24 inches squared times 20 inches is going to be 1,004.8 inches cubed. What do you think? Good stuff? Oops, there you go. Thank you. And it doesn't even have to be a regular shape like these. We can look at some really ugly things. Well, yeah, I know. The one end was folded out instead of being folded in. Yeah. There's a reason I'm a math teacher, not an artist. Oops, try that again. Finding the volume of something like this. My base is now this messed up thing here, because that is what slides through, as you can see. So to find the area of the base, I gotta chop this up, probably like that. So I've got this first one, that's just 14 by 18, which is going to be how much? 256, 52, 252. Somebody double check me.
Yep.
252, okay. Then I've got this second one here. This dimension is going to be how much? 14 minus 6 gives us 8 inches. This dimension is going to be how much? Yeah, 28 minus 18 gives me 10. So that will be 8 by 10, or 80 square inches. And now since this is 8 across here, because it's a rectangle, this is now 4. So that's pi times 4 squared divided by 2, because it's only half the circle. So 25.12 inches squared. So that's 357.12 square inches, correct? Okay. So now my volume is 357.12 inches squared times 30 inches, which is that 10,713.6 inches cubed. What do you think? Good stuff? Now, along with volume, we worry about density. Density is the mass of an object divided by the volume of the object. Basically, it's determining how tightly packed it is. So let's say we have 8 pounds of material and it has a volume of 2 cubic inches. We divide that out. Mass divided. Now, of course, mass is not really measured in pounds, but we tend to use pounds for both mass and weight. Technically, mass is measured in slugs. But slugs is a unit most people outside of engineering has never heard of. So we tend to use pounds for either one. So anyway, 4 pounds divided by 2 inches, 8 pounds divided by 2 inches, 8 divided by 2 is 4. And the units is just pounds per cubic inch. It's a relatively dense metal. Now the other thing you can do, for example, most woods, depending on how heavy or light they are between 25 and 45 pounds per cubic foot. So let's take a standard hardwood of 38 pounds per cubic foot. And let's say I have a project that's going to require 24 board feet. So 24 board feet is 2 cubic feet of wood. It's going to require 2 cubic feet of wood. The mass of that can now be found by just rearranging this formula. The density times the volume. So my 38 pounds per cubic foot times my volume of 2 gives me 78 pounds, is what that's going to weigh. if it contains 2 cubic feet of that wood. So this is used a lot in metal design. Let's say that you have a shaft that you're going to design, and you're trying to decide whether you're going to design that shaft out of steel or aluminum. And because of the strength aspect, steel would require 4 cubic inches of material. Aluminum would require 11 cubic inches of material. It's going to have to be considerably larger to handle the same amount of force. But let's say that steel has a mass of, what is it, about 2.8 pounds per cubic inch, and aluminum is about 0.9 pounds per cubic inch. So trying to figure out which one is going to be heavier, going to add more weight to the machine. Well, the steel, volume times density or density times volume, 4 times 2.8 is 1.12 pounds, or 11.2 pounds, right? 11.2 pounds. For the aluminum, it's going to be 11 times 0.9, or 9.9 pounds. So the aluminum is going to add, even though it's going to take considerably more of it, almost 3 times more, it still adds less weight to the overall piece. Now there's also price considerations. I've seen it where the aluminum actually still, because it has to be so much larger to get the same strength out of aluminum, it still may weigh slightly more, but aluminum is less per pound, so it's still cheaper to build it out of aluminum. So there's that consideration as well. So anyway, it is time to turn you guys loose. In your little book, it is Unit 31. In the big book, on page 251, it is exercise 8-7. I think that's 1 through 19. And on page 252, it's exercise 8-8, which I think is only 1 through 6. Have fun.